Hello, everyone. Welcome back to Theo-MathProblemSolver. In today's episode, we are going to look at finding the derivative of a function using the product and then the quotient rules. Then we'll look at situations where all these rules can be applied to real-world situations in economics, directly in relation to the average cost, the average revenue, and the average profit. If you find this content useful, please again subscribe, like, and comment, and as well share the content with other colleagues. Now let's get started. Hello everyone. So today we are looking at the product rule. So if I give you two functions and I ask you to find its first derivative, how do you find it? Remember, we said that derivative is the change in the function as a result of a change in the input. In other words, a change in the output with respect to a change in the input. So now if I have two functions and I want to know how these two functions are changing, but they are not just these functions, they are just a product, okay? So we are just finding their product and then kind of looking at how they're changing with respect to a change in the input. So that's what we are looking at. You know, such concepts sometimes can be very confusing, but I'm going to break down the concept into easy to follow, explanation. So take your time even as we explore it together. So if I have a function, so let's write that let big x being defined as small f of x multiplying g of x. And the question is, how do I find its first derivative? Okay, how do I find its first derivative? So that's what we are looking at. So I've employed with a technique that I term it as what we call the cover up. Okay, so I have a technique that I use to explain this concept, and I term it as cover up. So in differentiating this product function, okay, the product of these two functions, in differentiating it or finding its first derivative, this is what we do. So first, let's apply the differential on both sides, okay? So first, let's do this. Now, this is what I'm going to do. I'm going to cover the f. So first, I'm going to cover the f of x. So by covering it, it's as if I've used my hand to cover the f of x, okay? And now I'm now going to concentrate on the g of x, okay? Let me say that again. For me to find the derivative of this product of two functions, so first, let's cover the f of x. And by covering f of x, it's almost as if I'm placing my hand on the whole of f of x. So now, I'm now going to differentiate only g of x, okay? So I am kind of bringing the f of x, then now differentiating the g of x. Then, so with multiplication usually moves with addition. So I'm going to say plus, okay? So I'm going to say plus. Remember, first we covered the f of x, okay? So now we are going to cover the g of x. So take note. So now we are going to cover the g of x. So let's take note. So let me use a different pencil here. So I'm going to mean that now I can bring the g of x outside, then differentiate. Now the f of x. Please we all get it. So the first thing I did was to cover the f of x, okay? So by covering f of x, it means I'm now going to focus on the g of x. Then since we are talking about multiplication, I bring the addition, okay? Good. Then plus, now the second thing that I do is that I cover the g of x. I cover it, I place my hand on it, then I differentiate the f of x. So let's take note. Now we know that what's the derivative of g of x? G prime of x, okay? The prime I said is the same as derivative, okay? And then then we do the same thing for the derivative of f of x, and that becomes f prime of x. Good. So that's the theorem that I want us to embrace, that anytime you have the product, you have the product of two functions, then you want to find its derivative. This is the procedure we follow. Okay, but there's a trick, and the trick has to do with the cover. You cover one function, then differentiate the other, plus what we differentiate the function that was initially covered, and we cover the other. So I want us to kind of take note. And so at this point, let's see how best we can sort of employ such strategies to solve problems. Okay, so let's go to the first example. So with the first example, so let me give you a very nice example. So the first example, so let me give you, if I ask you to find the derivative of, so we have such function. How do I solve this problem? Well, by applying the same rule. Okay, how do I solve this function? How do I solve this function? This is one function, so let me write down function. So let me write down the function. Okay. This is our function that is a function that we have. Okay, you want to find its derivative. So now the question is that how do I, so these are two functions. So we assume that this is one function and that this is a different pencil, this is another function. Okay, so let's call this one, let's suppose this is our first function. That's called the f, and this is our g. Okay, and these two functions are multiplying. And the question is, how do we, invoke the theorem we have, already established? Now, this is how we do it. We said that we use the cover. So first, this one is up to you. Which function do you want to first, cover? Which of the functions do you want to cover first? So first, let's cover the f. Okay, so by covering f, it's almost as if you have placed your hand on f. So it's almost as if you are blind to the function f, now concentrating on g. So it means that you're going to have, if I'm covering the f, it means that f will stand outside, and now I'm not going to differentiate the g. Okay, plus now I cover the g, and now I'm not going to differentiate my f. Is that okay? So it's a technique that we use now, which means that wherever now I just have to do my substitution, then I go my way, right? My f, I know that it is x to the power 4 minus 2x to the power cube minus 7. Then I differentiate. What is my g? My g is this expression, okay? And where's my g here? What is my g? My g is what? 3x squared minus 5. So over here, what we are doing, we are just taking our time to just learn the basis. There'll come a time where I'll have to speed up a bit, okay? But this is just a first example, so I'm taking my time so that everybody will understand this. If you have any questions, please put it in the comment section and I'll attend to you guys. Now, when we differentiate, so now we are differentiating the first expression, the first function. So we are differentiating x to the power 2 minus 5x. Now when we differentiate 3x squared, what do we get? So we drop the 2, we subtract 1 from that, right? So we drop the 2, and that gives us, well, 6x. And then, taking 1 from the 2, that gives us 1, right? And when we differentiate 5x minus 5x, we get what? Minus 5. Good. In case you missed the previous videos on how to kind of, find the derivative of simple functions, just follow the previous videos. It kind of highlights on all of these things. So let's take note. And then the derivative of x to the power 4 is what? 4x to the power 3. And the derivative of 2x cubed will give us what? 6x squared, right? Good. So let's take note. So this is as simple as that, okay? However, at this point, somebody can decide to expand and simplify. At this point, I don't think it's necessary for us to do that. This is very simple. So let's look at one more example, just for us to really understand the concept well. So what if I give you that, if I ask you to find, so for instance, if I give you y equal to root of x plus 1, and then the fifth root of x minus x, okay? So let's look at how best we can solve this. If I ask you to find y prime dy dx, or this is the same as y prime. Okay, good. I want us to try out this. What do you think we will get? We can, at this point, I want to pause the video and try it out, and let's see what you get. What do you think we will get? So by using the same principle, we do what we call the cover up, right? So we can cover the first function. So we can assume that, so at this point, we can assume that the first function is our f, and then at this point, we can assume that the first function is our f and the second is our g. So we can kind of do that. So we can assume that, so let me make it simple. So we have something as this, and then the fifth root of x minus x. So let's take note. Now we can assume that this is our f, and then this is our g. Okay, good. So since we've already established that, we can just go straight to the point. So we have our dy with respect to x. as changing y with respect to, I said derivative. Derivative means changing the output with respect to changing in the input, okay? Or changing in the function with respect to a change at some point, okay, over time. Very good. So I want us to take note. So by employing the same principle, you're going to have something beautiful as this. Then we differentiate the fifth root of root of x minus x, then plus. And as I mentioned, the multiplication always moves with addition. So take note that, and that we are going to have something as this. Now, over here, we kind of go straight to the point, and that should give us, when we differentiate the first one, we are going to have what? Remember the power rule. With the power rule, we kind of said that we, this can literally be written as what? X to the power of 1 over 5, right? So let's take note. And this is the root of x is the same as what? X to the power half, right? So I want us to take note of that. Now, what is the derivative of x to the power 1/5? So we drop the power, and that gives us what? 1 over 5, then multiplying what? The x to the power, then you subtract 1 from the power, and that gives us what? Minus what? So let me be more specific. Let me take my time over here. I'll subtract 1 from that. And when I differentiate minus x, I get minus 1, right? So over here, let me take my time so that everybody can understand it very well. And when you differentiate, root of x is to the power half, right? It's the same as root x to the power half. So let's say, so when we do that, we are dropping the half, then we subtract 1 from the half. So we subtract 1 from the half, okay? But when you differentiate a constant, you get 0, right? Good. So let's take note. There's a reason why I'm taking my time. It's for those who could not follow the previous. And just to have an in-depth knowledge on the previous content, you may have to take your time to, go through it so that you can appreciate what we are doing well. Now I can just invect it, and by invecting, I'll get something as nice as this, okay? So let's take note. So this is how far we would get over here. I think you can still expand. At this point, I don't think by expansion it will really make much sense. So we'll leave answer as it, and we can look at something other interesting stuff, okay? Good. So I would want us to see whether we can look at other interesting example. However, if you have any question, please put it in the comment section. And so I would want us to look at the quotient rule. In the previous section, when we're talking about limits, we talk about the quotient rule. And now, how do we find the derivative of quotients? Okay, how do you find the derivative of quotients? Now, if two functions are kind of dividing each other, or one is dividing the other, how do we find its change with respect to its input? Okay, how as it begin to change, how do you find a derivative? There's a simple trick that we use to do this. So today I'm going to take my time to also make it, to kind of have a glimpse of what goes into the quotient rule. So I'll take my time to explain it, then we'll solve 1 or 2 examples so that you embrace it more. So let's look at, so if I give you, so if, okay, so if or suppose Q of x is equal to this quotient, okay? So the n, suppose the n is the numerator and d is seen as the denominator, and then it is easy for us to kind of relate it, okay? Good. Now, for us to find the first derivative, or just the derivative, or to find a differential, what we do is that, so first, what we do is that, so we are seeing that square the denominator, okay? So first, so square the denominator, okay? Then what we do is that, because we have squared the denominator in the numerator, what we do that we are going to keep it at the first instance, and then differentiate the numerator, okay? Now, with quotient always goes with subtraction, so we say subtraction. So we kind of use subtraction for that. So let's take note. And then remember that in the first instance, D was covered. It's almost to see D is covered. Okay. Now let's cover the N. Okay. So you're going to cover the N, then differentiate the D. Is that okay? So that's a trick that we use. The first thing we do is that square the denominator, which is D of x, we square it, then we cover it in the numerator. Okay. Then we multiply it by when we differentiate the numerator. Then since we are talking about the quotient, you bring the subtraction. Then remember, the first time D was covered, now it's not, it has to be uncovered, okay? By uncovering it, we differentiate it. Is that okay? Good. So at this point, let's look at some nice examples so that we appreciate it here. Let me give you a sample here just to see how you can. So if I to differentiate, let's say g of x equal to x squared minus 3x all divided by x minus 1. If I to differentiate it, what do we get? So at this point, you can pause your video and then try it out, and let's see. All right, so let's go. So we have g of x mean as this. So now it means that our g of x, this is also the same as what something as this. So let's take note. So now what did we say? Suppose so we claim that this is our n of x and this is our d of x. So let's take notes. Now we said that for us to find the of this quotient, what we do is that we keep the denominator, okay? And denominator is this. Then what we kind of square it, okay? Then over the numerator we keep it. Then we differentiate our n, okay? Then we subtract since we are talking about quotient, okay? And then since in the first instance we kind of differentiated the n, now at this point we're going to maintain it in order to recover it, then differentiate our d of x. Okay, by applying the same principle here, remember what we're going to do is to do our substitution, because now we know our n and our d. So what our d is now x minus 1, and the function we're trying to differentiate is what? X squared minus 3x minus our n is what? X squared minus 3x, and then our d is what? Our d is what? X minus 1. Good. All divided by our d. Our d is what? Is x minus all to the power 2. Good. Now let's simplify this. Let's differentiate and simplify. Now when you differentiate x to the power 2, we get what? We get 2x. And when you differentiate 3x, what do we get? We get 3. Good. And when you differentiate x, the last time we said we get 1. And when you differentiate 1, we get minus 1, we get what? 0. So let's take note. Now at this point, we have to expand and simplify. Now when you expand and simplify, you should be able to get something beautiful as this. Okay. So now this is our g with respect to changing g with respect to changing x. So this is our result for this particular problem. So that is it. So let me give you this problem to solve. If I ask to show that when we find the derivative of such a function, such quotient, let me take my time and write the function well. All right, so we want to show that the derivative of such a quotient is this result, okay? How do we show this? Now, by following the same principle or the same rule, we should be able to solve this problem. Now, we are given such a nice function, such a quotient to solve. How do we solve this? So we can assume that this is our n and the whole of this is our d, okay? So by applying the same principle, we keep the denominator, and the denominator in this case is our x plus 1. Then we said we square it, okay? Then in the numerator, what we do is that we keep it first, then we differentiate the other function, which is what? Ax plus 1. Then since we are talking about quotient, what do we subtract, okay? Good. And then we kind of we keep the ax plus 1, then we differentiate, okay, the d, which is bx plus 1. Now at this point, when you expand and simplify, you should be able to get, what do you think we should get? That should give us what? Bx plus 1, and that multiplying a, because we know that the derivative of ax is a, and then the derivative of 1, which is a constant, is 0. Okay, so then we have something as what? As this. Right? Now, when you expand and simplify, you should be able to get something like what? Abx minus b all divided by bx plus 1 to the power 2. And that should eventually give us what? So when you do your cancellation, you should be able to get what? A minus b all to the power of bx plus 1 all to the power 2. So now we've been able to solve the problem. Very good. So you can compare your result to what we have and see. All right, so let's look at these definitions. And these definitions are going to be very helpful as far as our discussion is concerned. Now, if C of x is a cost of producing x items, then what then becomes the average cost of producing x items? So for us to do that, it's just going to be the cost function divided by the number of items that is being produced. Now, if the R of x, which is a function, is a revenue from the sale of x items, then the average revenue from selling x items, which is going to be the revenue function all divided by the number of items that are being produced. And if P of x is a profit from the sale of x items, then the average profit selling X items is a ratio of the profit to the cost of producing X, or sorry, the number of items that are being produced. Okay, so let's take note. But then I want us to kind of try to see how best we can analyze these definitions and make a meaning out of it. All right, so let's look at this nice and interesting problem. So Paulson's greenhouse finds that the cost in dollars of growing X 100 geranium is given by such function. So in other words, this is our cost function. If the revenue from the sale of X 100 geraniums is given as this. Now, how do you find each of the following? So first, the average cost. How do we find the average cost? So let's take note. How do we find the average cost? So the average cost, I'm going to use AC, okay, or A subscript C to represent the average cost. So average cost, we said, is a what? Per our definition, average cost is a cost of producing, is a what? Is a cost of producing X items, okay? They're all divided by the number of items that have been produced. Okay, good. That's what we said. So average cost. So I'll use the word out. Let me just make it simple that the average cost. So average cost is just going to be the cost divided by X. Is that okay? It's just going to be the cost. And in this instance is what? It is being represented as what? Which is C of X or C of X. Okay, so it is C of X or divided by X. So let's take note. Now, what is the cost in the given function? The cost is given as what? As 200 plus 100, all multiplying the fourth root of X. Okay, then all divided by X. Now, how do we find the average revenue? So the average revenue, if average cost is equal to cost over X, what then becomes our average revenue? So our average revenue is just going to be what? Revenue over X. Okay, so let me use this pencil. So average revenue is always going to be what? Revenue over cost. Sorry, it's just going to be the revenue over the number of items that are being produced. And the average cost is just going to be what? Cost over the number of items that are being produced. So I want us to take notes. What about so this, we are still on the A part, yes. So what about if I ask to find the average profit? So if I ask to find the average profit, so the average profit would just be what? That's going to be profit, okay, over the X. Good. So now we know kind of, what is profit? Profit is what? It's always equal to what? Your revenue minus your student. So your profit, we know that from economics or accounting, we know that revenue will always be, so our profit will always going to be our revenue minus our cost, right? Good. So now the B part, now with the B part, now this is our A part, okay? The A part, we are done with it. Now, how do we find the B part? So the B part says that we find the rate at which the average profit is changing when 300 geraniums are being grown. What is the average profit? Already we know the average profits, okay? So now first, so the average profits, now we know, let's put in the formula, but over here already we know the functions, the various functions already. We know that the average profit, let's denote it as AP, is equal to what? Your revenue minus your cost, all divided by X. And then the question is, what's our revenue? The question, our revenue is what? 20 plus 90, or multiplied root of X. And what's our cost? Our cost in the question was given as what? 200, all divided by X, right? Good. When we further simplify, we should get something like minus 80 plus what? Fourth root of X, all divided by X. I would want to mention over here, we use minus, and then we kind of use the bracket, because remember, the CX is a function, so you may have to make sure you bring a bracket, just in order not to cause confusion. If you don't bring a bracket, you would kind of make mistakes, so take note of that. Now, remember, we are looking at the rate at which the profit is changing. So let's take note. The rate at which a profit is changing means that what? You have to find the first derivative. So what then becomes the derivative of the average profit with respect to X? Good. How do you find that? So which law or which theorem should we use here? The quotient theorem. So suppose this is our n of X and this is our d of X. So we are going to invoke the theorem on the quotient function. Okay, good. So we said that we keep the denominator, so we keep our x at denominator, then we square it, then we keep it at the top, then we differentiate the numerator, right? Good. So let's take it. We're going to differentiate. Our numerator is what? Minus 80 plus what? 90 root of x minus and the fourth root of x. Then we differentiate our x. So let's take note. Then when we differentiate and simplify, we should get something as what? Now we know how to do all of this. So I will not waste my time here. So this, I'll go straight to the point because we solved so many examples. So we are now comfortable and familiar with such stuff. So we should get something as this, and all divided by what? X squared. I think that we can still simplify, yes, because we see that certain things can be simplified. So we can simplify something as this. No, let's first, before I do what I'm about to do, let's simplify this a bit, and that should give us something as this. Now, when you look at the question, it says that you find the rate at which the is changing at a point where, we have about 300 geraniums, right? So that is the way the question is kind of about. So we're going to evaluate the average profit at x equal to 300. So it just means that wherever I see 300 in this result, we should replace it by 300. Okay. So with 300, we get something like this, and the result, when you use a calculator to punch in, it should get something like 11.196. Okay, dollars. So which means that at 300 geraniums, Paulson's average profit is increasing by about 11.20 per 11 point, which is approximately when you kind of do your rounding, you should get approximately 11.20 per plant. Okay. So I want us to kind of take note. So at this point, if you have any questions, please put in the comment sections. And as I mentioned, always, I bring in the best content on calculus, and I would want you to subscribe. Find it very helpful. Share it to your colleagues, your loved ones, and let's keep spreading the good news. Thank you.